exponential functions, differentiation, and integration. We here really introduce how to calculate the derivative on the exponential function e to the x. Previous section we looked at the inverse of a function. So we talk about the inverse of e to the x as being the natural log of x, and then likewise the inverse of the natural log of x is e to the x. And so we recall from algebra how the connection between the natural log of x and e to the x have been displayed. This section, 75% of it, 60% of it is a review from algebra dealing with exponential functions. And so you can see how e to the x and the natural log of x, how they're inverses. And if you take the line y equal to x, you see how these two functions are indeed symmetric with respect to the line y equal to x. And how the inverse properties and the relationships relate one to another, that the natural log of e to the x is x, and e to the natural log of x is equal to x. And so this follows f composed with g evaluated at x is equal to x. And so, and then vice versa, g composed with f evaluated at x is equal to x. So they satisfy the property for the inverse. Again, more algebraic operations of exponential functions. This is a review. Now the derivative, I thought was interesting. The derivative of e to the x with respect to x is equal to e to the x. And then the derivative with respect to x of e to the u is e to the u times the derivative of u. Well, let's look at the proof, if you will, of the first one. So here, let y equal to e to the x. And we know that direct implication, that the natural log of y is equal to the natural log of e to the x. And we know that here the natural log of e to the x is equal to x. You can write this as x times the natural log of e. The natural log of e is equal to 1. So this is x. So what we have now then, is a period, is the natural log of y equal to x, differentiating both sides. This yields for us too much. This yields for us here. I better say it like this. This is the derivative with respect to x. The natural log of y is equal to the derivative with respect to x of x. So this gives us 1 over y times y prime. That's equal to the derivative of x is 1. So we end up with y prime is equal to 1 times y, which we get y. But it's not a good but. Well, you know what I'm saying. You know what I'm saying. But y prime was what you were after, right? Y prime is dy over dx. And y was what you wanted from the beginning, right? Y is e to the x. So here, dy over dx is the same thing as the derivative with respect to x of y. What is y? E to the x. as equal to e to the x. So the proof makes sense that the derivative of e to the x is indeed e to the x. And then if u is a function of x, then obviously you get here e to the u times the derivative of u with respect to x. In terms of the integration is straightforward, that if it's the integral of e to the x dx, the result there is just e to the x plus c because of the inverse property of the derivative and the antiderivative. Now, be careful with the integral of e to the u du. What this means is that the derivative of u has to exist somewhere in the integrand with respect to du, and so the result would be e to the u. I didn't see a problem of such on that. Maybe I can put an example here. I did not think about it until now, but if you have the integral of e to the, let's say this is x squared. Oh, I got to have an x down there to have a u du, so nothing that difficult. Let's say this is 5x, e to the 5x dx. That's good. Now, the answer is not e to the 5x plus c. No, because here, this 5x is a u. So here, we have let u equal to 5x, du is 5 dx. So watch this. So now, 1 over 5 du represents dx. This dx is this dx here. So that dx is 1/5, let's put it right in front, times the integral of e to the u du. Now this result is 1/5 times e to the u plus c. Put that in a bag. So the result we get is 1 over 5 times e to the u plus c plus sign. But this is 1/5 e to the u is 5x plus c. So what I'm saying is you want to be careful when they talk about this u and du. They're saying something, right? They're saying a whole lot, that u is a function of x. It's just not one term there. It's a term whereby you have to use some type of u du substitution, and that's what they're begging for. So just make sure that you watch out for that. So now here, just for a while, you can forget about calculus and say, for this, solve for x accurate to 3 decimal places. Now e to the natural log, they're inverses of each other, so this leaves the term 3x. Here that's equal to 24. X is equal to 8. Again, no calculus. Here, solve for x. Let's add 12 on both sides, so you get e times 8 times e to the x is equal to 19. E to the x is 19 over 8. Take here the natural log of both sides, so the natural log of e to the x is equal to the natural log of 19 over 8. So x is equal to whatever that is, and since they want the decimal, you get 0.865. It's approximate. This is not exact. This is exact. This one we solve for x, multiply both sides by 1 plus e to the 2x, divide both sides by 2, and so we have 2500 is equal to 1 plus e to the 2x. Subtract both sides by 1, get 2499 is equal to e to the 2x. Again, these are things that we've done in the past. Take the natural log of both sides, divide both sides by that 2, you get the result. This is the natural log of 2499 is equal to the natural log of e to the 2x, which is just 2x. Divide both sides by 2, so x is equal to, here is the exact number, the natural log of 2,499 divided by 2, and it's approximated by 3.9112. Here, this is an equation involving a natural log. We use the inverse property and exponentiate both sides. So this gives us x minus 3 is equal to e to the second. So x is equal to 3 plus e to the second. It's approximated, since they want the approximation, 10.389. Almost forgot what I said just that quick. Let's keep digging. Here we find the derivative. Yay! So y prime, the derivative is e to the u and then times the derivative of u. So this is the derivative of that negative 2x to the third times e to the negative 2x to the third. So y prime is negative 6x squared times e to the negative 2x to the third. Here, the derivative there, we use the product rule, so we get 3x squared times the second plus the first times the derivative of the second. Well, the derivative of e to the x is just e to the x. Now you can leave it like that, or you can just simplify it, factor out the common terms. The common term is x squared. Dad blasted. X squared e to the x. You have left 3 plus x. Take this derivative. We use the chain rule or the power rule. So this is 3 times e to the negative t plus e to the t times, we'll raise to the second power, times the derivative of the inside. Let me start with this e to the t. The derivative of e to the t is e to the t. The derivative of e to the negative t is negative e to the negative t, right? It's e to the negative t times the derivative of negative t, which is negative 1. So this is minus e to the negative t. Take the derivative of this guy. This is y prime is equal to 1 over 1 plus e to the 2x times the derivative of 1 plus e to the 2x, which is just 2 times e to the 2x. The derivative of 1 is 0. The derivative of e to the 2x is e to the 2x times the derivative of 2x, which is just 2. So here y prime is 2 times e to the 2x all over 1 plus e to the 2x. Just one more here. We use the quotient rule, the derivative of the numerator, which is just e to the x, times our denominator, minus the numerator, e to the x plus 1, times the derivative of our denominator, which is just e to the x, all over our denominator squared. So y prime, this is e to the 2x, would cancel out with e to the minus e to the 2x. You see it there. Minus e to the x. This is minus e to the 2x minus e to the x all over e to the x minus 1 to the second. So these terms there cancel. So y prime is negative 2 times e to the x all over e to the x minus 1 to the second. Well, I think that should do it. Thank you.